Okay, we're finishing the proof of Kaplansky's density theorem, and what we need is the following level. If f is a function from the reals to the complexes, is continuous and bounded, then the function sending t to f of t is strongly continuous on the set of self-adjoint elements in P of H. And the way we're going to do this is our approach is that we will define S to be a set of functions from R to C such that T maps to f of t. Well, I mean, I guess I should say that f is continuous such that t maps to f of t is also strongly continuous. So that's just a definition. We will prove that the bounded continuous functions on R is contained in S, right? So that's how we're going to work this. And so, change to black. So the proof is sort of a proof in many small steps. First, let's define two concrete functions, g of t, so these I'll call them g and h, and they will be bounded functions on the reals with complex values, but actually they'll be real valued. So the one that I'm calling g of t is t over 1 plus t squared, and the one I'm calling h of t is 1 over 1 plus t squared. It's called f in Longfield's proof, but I think that's just asking for trouble because all the functions are called f here. So, so let me just give you an idea of what these functions look like. So the graph of g looks something like, again, have a, so something like this, and the graph of h, it looks something like this. So these are two concrete functions, and we're actually aiming to prove that they lie in S, but that's gonna take a little while. So the first part of my proof, I will prove that first of all, the function which is constantly 1 and the function which is the identity and also g of t, they all lie in S, right? So apart from the two concrete functions that I've looked at, we also have the identity, and t, and of course the graph for the identity looks like this, and the graph for t, of course, looks like that. Right, so these, I'm claiming that all these four functions are in S, but I'm only going to prove it for 3 of them. Right, and it's sort of obvious that if I take the function which is constantly 1 and apply it to t, I just get the identity of p of h. So that's a constant function, so of course that's continuous. And if I take the identity function applied to t, I just get t, so it's the identity function, so of course that's continuous. But with g we have a little bit more work. So I will look at g, let's assume that t alpha converges strongly to t. Everything is self-adjoint. And now let's look at g of t alpha minus g of t. And I will write g of t alpha out. I'll do it in a slightly clever way. So I will take 1 plus t alpha square inverse t alpha. That's the way I'm writing g of t alpha. And g of t I'm writing as 1 t times 1 plus t square inverse. Right, so first of all, we've seen that, I mean, it's clear that g of t is t times h of t, right? So I can, instead of applying g directly to t alpha and t, I can take the identity on t alpha, which just gives me t alpha, of course, and then h of t alpha, which is this inverse of 1 plus t alpha squared. So, and you know, I'm using that the functional calculus will give me the inverse of 1 plus t alpha, because when I multiply it by 1 plus t alpha, I get the identity. Right, so this is sort of just set up. Why am I writing g of t alpha and g of t out in 2 different ways? Well, first of all, I'm allowed to, because of course t alpha commutes with anything that I can build from the identity in t alpha. So does t. So I mean, I'm just using this, doing this because it's nice for my computations, and of course I'm allowed to do it because the elements can commute. So now I will write, this is a kind of a trick that we used in the very beginning of the course. I'm going to write the difference as something like this. So I will just write t alpha 1 plus t square minus 1 plus t alpha square times t, and then 1 plus t square inverse. Right, so maybe do some highlighting here. So what is it that I've done? I've collected all the terms in 3 terms that I'm multiplying. And so, for instance, if we're looking for the term here, where is that? Well, I get that from taking this term and this term and that term, because the I plus t squared inverse cancels out with the I plus t squared. Right, and of course, this term here, where is that? Well, I get this by this term and that term and this term, for the same reason as before.